let's talk rocket science, or more specifically, let's talk about the ideas of applying momentum conservation to an isolated system that is not closed. Now, a closed system is one where the mass of each element remains constant. An open system, then, is one where the mass is changing. And that is exactly what's happening when we take a look at what's going on with the rocket engine. Essentially, a rocket engine is a controlled explosion that is continuously changing the mass of the rocket as a whole. And for our analysis, we're going to make two assumptions. One, we're going to assume that the rate of fuel consumption, which is minus the derivative of mass with respect to time, is going to be a constant. The other thing that we're going to assume, if we take a look at the relative velocity of each tiny particle of mass with respect to the craft, that relative velocity is going to remain constant. So if the first molecule of gas exits the thrust nozzle at 1,000 meters per second down, all of those are going to leave relative to the velocity of the rocket at 1,000 meters per second down. So essentially, if the rocket were moving at 1,000 meters per second up, that particular particle of exhaust would be stopped. And then any exhaust above that speed is still going to be going up, but slower. So, if we take a look at this rocket thrust, I said it's just a controlled explosion. And an explosion is a collision done backwards, which means even though we have a non-closed system, we can still apply conservation of momentum. So the initial momentum of our system would have to equal the final momentum of our system, and let's say that we basically start with a rocket that happens to be not moving. So that means that our total momentum would be 0. So that would then, after the explosion, equal the momentum of the exhaust that we have traveling out of the back of the rocket engine, plus the momentum of the rocket post-exhaust. Well, the momentum of the exhaust is just going to be the mass of the exhaust, which I'm calling dm because it's a pretty small infinitesimal amount of mass, times the relative velocity. And the mass of the rocket is going to be different. It's going to be the original mass of the rocket minus the amount of mass that we lost as exhaust, and then that gets multiplied by the infinitesimal gain in velocity from that small patch of mass getting exhausted out the back. Well, I could distribute that out, and I would have the mass of the rocket times the tiny change in velocity, and then I get two infinitesimals. And an infinitesimal times an infinitesimal, we're going to say is equal to 0. It's really, really tiny, and we're going to be able to ignore it. Well, if that's the case, then this plus mass times the change in velocity equals 0 means the mass of the exhaust, infinitesimal, times the relative velocity of the exhaust has to equal minus the mass of the rocket times the infinitesimal amount of velocity. So say we want an expression for Newton's law, an expression for the force. Well, the force on a rocket should be the mass times the acceleration. Well, if I divide by an infinitesimal amount of time, on the right I get minus the mass of my rocket times dv dt. That would give me the mass times the acceleration. And I'm going to take this minus sign and move it to the other side. Well, here I would have minus the change in the amount of exhaust. Well, minus the change in the amount of exhaust is exactly the change in the mass of the rocket with respect to time. So, to calculate the rocket force is the rate and change of mass with respect to time of the rocket times the relative velocity of that exhaust gas. And that equals the mass of our rocket times the acceleration. So, let's take this framework and let's get rid of that dt again so we can actually take a look at calculating changes in velocity. So, if the change in my mass divided by time times my relative velocity is equal to the initial mass times the derivative of velocity with respect to time, well, that dt could cancel back out, and then I could divide both sides by the mass of the rocket. And that tells me that the infinitesimal change in velocity of the rocket would be equal to the relative velocity of the exhaust times the infinitesimal change in mass divided by the current mass of our rocket. So to find our total change in velocity, I integrate both sides, and that tells me that my change in velocity is equal to the relative velocity times the natural log of the final mass divided by the initial mass. Well, rockets always lose mass, which means this ratio is always going to be smaller than 1. So what I could do is play fun with natural logs, and I could flip the order of the ratio. And if I flip the order of the ratio, the log of the initial mass to the final mass is always going to be a positive number, but that means I need to throw a minus sign out in front. So our velocity changes in the exact opposite direction of the relative velocity of the exhaust escaping our rocket, and the amount of change of velocity we have is based on the natural log of our initial mass to final mass times that relative velocity. Thanks for watching.